Hello out there, this is Scott, and today I'm going to show you how to deploy a column-safe file system with the new Pulumi-based deployer. All right, so agenda for this demo session. First, we'll see some references on the QSFS documentation, QSFS repository on GitHub, tell you a bit about the column-safe file system and also Pulumi. And finally, I'll show you a demo. All right, so link is here. We'll actually take a look at those a bit later, but let's get into the presentation now. So QSFS, also known as column-safe file system, is a distributed storage system that uses a Fuse file system frontend and forward-looking error-correcting codes to distribute data among a set of backends. It can be configured to tolerate the loss of X backends or Y groups of backends without losing data. So QSFS system is pretty flexible in terms of how you set it up, but when I'm talking about backends, those are generally going to be individual nodes, individual machines. And when we talk about groups, these could be like groups of machines in the same physical location. So that means you can set up the system to tolerate the loss of, say, up to 5 machines within a given physical location, or tolerate the loss of an entire physical location if you have 2 or more, and then also tolerate the loss of machines within those. So there's a variety of ways that you can set this up. Today I'll be showing a pretty simple example. All right, Pulumi, what is it? It's an infrastructure management platform to automate deployments through infrastructure as code. It's somewhat similar to Terraform with some differences. The main difference being that you can configure Pulumi in any programming language that you like, and that means you can add sort of additional logic and additional automation also in that language. So the deployer that I built for QSFS is done in Python programming language, in Pulumi using our Pulumi plugin. And that's allowed me to also do some automation, post-deployment automation that sets up the QSFS instance. So most of what I need to do to get this up and running is fully automated, thanks to Pulumi and Python code. All right, quantity storage system, key concepts. I'm not going to get into all the details. If you're curious to know more about the inner workings, there is information in documentation about the various components, how they work together. But here it is at a high level. So our front end is a Fuse file system, usually backed by solid-state disk. In this case, it's going to be running in a virtual machine that will deploy on the ThreeFold grid. This doesn't have to run in a VM on ThreeFold grid. It can run in any Linux environment, but you do need a Linux environment. All right, so our backends are ZDB, and in this case, we're using a primitive offered by COS. These ZDBs are backed by HDD hard disk. You can supply your own ZDBs, and those could be backed in theory by solid-state disk. But this is the most economical way to do it, both because hard disks are cheap and also because when we use the primitive from ZOS, we only need to reserve that hard disk space. We don't need to reserve any compute, so any CPUs, RAM, or solid-state disk, say to back a VM that we could put a ZDB inside. So HDD, we can just reserve it from ZOS as ZDB space, and that's all we need to pay for. The total stored size can exceed the front-end size, so we can have more data than what the front end can hold, but you can also have a front end that's big enough to hold all of your data. That's up to you. But if the total stored size is going to exceed the front end, that front end will always retain the most recently used data. It will delete any older data and the most oldest data from the system. And if that data is needed again, it will pull it in from the backends and reconstruct it. So that happens automatically as needed, the removal and rebuilding of that data. And what this also means is that if you lose your front end, that data can again be restored from the backends. The Pulumi-based deployer helps to restore that front end, assuming that you are using a VM on ThreeFold Grid. There's some documentation about how to do that. I won't show that step today, but what I will show is how we can replace individual backends to restore our backend configuration to the desired amount of redundancy if we happen to lose backend. All right, and finally, the quantum safe aspect is that the data is encrypted and sharded before sending to the backends, which means that even with a quantum computer or some device that can break this encryption, there's not a chance to decode or recover data from those backend machines. So this means that we don't need to trust the backends, and we can, in this case, use any machines that are available on the ThreeFold grid. For today's demo, I will be using our free farm that ThreeFold operates. But you can choose any nodes with hard disks, and you can find those nodes using the dashboard. Yeah, so find some nodes that you like that are in physical locations, or farmers that you know, things like this. And you'll need that list of nodes as one of the prerequisites for creating your deployment. I won't show you that all the steps of how to search for nodes and things like that. There's documentation in the manual about how to use the dashboard, and it's pretty straightforward. All right, so Pulumi deployer key concepts here. So this is a new way to deploy a quantum safe file system. In the past, you could always deploy it manually. We've also had a deployment primitive inside ZOS that you can deploy using, say, Terraform, or I guess also Pulumi. But that ZOS primitive did not fully expose the deployment to you, so there's some things that were difficult or impossible to do, such as replacing the backends or replacing the front end. So this Pulumi-based deployer, it automates the deployment, setup, and the maintenance using CLI tools. So you will need to be comfortable on the command line if you want to follow along. But it provides the ability to, well, as I was saying, replace the backends, replace the front end, basically do everything that you can do with a manual deployment. It gives you the full flexibility, but it's largely automated, so it makes things considerably easier than going through the steps manually. All right, let's get into demo. So first, I just want to show you a bit around some of the relevant repositories here. This is GitHub ThreeFold Tech Pulumi ThreeFold. This is our Pulumi provider. And I just wanted to show this in case you wanted to do anything with Pulumi yourself on ThreeFold Grid, or if you want to hack on the code for the QSFS deployer. You can find some examples in here about how to use Pulumi using the various programming languages that we support, as well as YAML. And so in this case, like we could check out this Python deployment, how to deploy a virtual machine. And this will give you a very basic example you can use to get started with Pulumi and Python, like I did for the deployer that I'll be demoing today. So that's here if you want to jump in, build stuff using Pulumi. It's pretty cool. And this is our repo for our provider plugin where you can find some examples. All right, so Pulumi. In this demo, I'm not going to show how to install Pulumi, but there are instructions here that you can easily find via a web search or coming to pulumi.com and following the links. So if you're on Linux like I am, you can copy this line, you can grab the binary for yourself. There's a couple of ways to install it. And if you're on Mac OS, you can install using Brew or also a binary installation. For Windows, there is an installer. There's also Chocolatey. What I would recommend if you have Windows is get yourself a Windows subsystem for Linux setup and then follow along with the Linux steps here. This might work on Windows, but I have not personally tested it, and Windows subsystem for Linux is pretty great these days. All right, here is the quantum storage repository on GitHub ThreeFold Tech Quantum Storage. This contains sort of some odds and ends like documentation, this Pulumi deployer script, some other scripts that are involved in making quantum safe storage work. It does not contain the code for the various components that make it work, though. Those are linked down here, along with some information about how the pieces fit together. And there's also some other scripts in here that can help you to spin up like a local, totally local copy. There's some stuff in here that's outdated, so don't watch your toes in here, but the Pulumi deployer is here under this Pulumi folder. So for documentation, it's going to link you over here to the docs tree. And this contains the most complete and up-to-date documentation we have for QSFS, including how to do a manual deployment. And the steps for deploying with Pulumi are covered here. So as I was mentioning, we'll need to install Pulumi on the system. We will need Python, of course, and there's a couple of config files that we need to set up. So once you have Pulumi and Python on your system, steps basically are to clone the repo, install the Python dependencies into a virtual environment, and once you've done that, you'll be ready to go and use Pulumi to execute this Python script that creates a deployment. So that's pretty straightforward. Once you've got Pulumi set up, basically just need to copy and run these commands. And then we'll need to prep our config files. These two config files are mandatory. There's also optional Prometheus configuration. And these config files both come with an example template. And what you can do is just copy the templates to the path that the deployer script expects and edit these with your favorite editor. So let's take a quick look inside of these config files. So the first one is vars.py, and this is where we pass in the information needed to create the deployment, things like our mnemonic seed phrase. So you will also need an account that is funded with TFT and verified. I won't cover all that, but you can go to the dashboard and get that set up. If you need any help, you can again check the manual. So here's where you can enter your mnemonic. You can also specify this as an environment variable, which is what I'll be using in the demo today. So this is just using the same name, mnemonic and network. You can use environment variables instead of putting your information into this file. So if you don't want to write your mnemonic into the file, use an environment variable. That can be nice because these files have a way of ending up in places that you didn't want them. So that might be a smart thing to do. All right, we'll also need to give the path to our SSH key, and this is the private key, because Pulumi will be using the Pulumi script will be using our SSH private key to do some SSH operations to finalize the deployment. After it creates that VM, it's going to run some scripts inside that VM and upload some files, and for that it needs our SSH private key. And then the public key that's associated with this will also be sent into the VM as an authorized key, of course, so that we're able to do that. All right. As I was mentioning, this deployer deploys a VM for the front end. So you enter the node ID of the VM that you want to deploy on here. You can also enter none, and that will skip the VM deployment if you wanted to use your own existing machine for the front end. In that case, you'll still need to set things up there. So that's a possibility, but what we'll be demoing today is the full deployment, including the VM. We need to specify some node IDs to deploy our ZDBs on. So these, again, should have hard disk. And I've given some example nodes here, which again are in free farm. the data size of each backend in gigabytes. So I didn't talk about this much yet, but the way that we configure our quantum safe storage system, in particular the way that we configure Zstor, will determine the amount of overhead. So we have a trade-off here. We can have more overhead, giving us more redundancy and more fault tolerance, or we can have less overhead, giving us less redundancy and less fault tolerance, but maximizing the amount of storage, net storage that we get for the storage that we're reserving. So here's where you need to specify the data size of each backend, and then according to how you have Zstor configured, which we'll see in the next file, that will determine how much net storage you're able to use, which basically the equation is like the number of backends times the size of each backend times the efficiency factor that is determined by how much replication we end up with. So in a typical setup, you might have like a 20% overhead or something like that. So you'd be like, in this case, we'd have 4 backends giving us 4 gigabytes. So let's say it's 25% overhead. And so our usable storage would be 3 in that case. That math you can figure out for yourself. The next thing here is how are we connecting to the backend ZDBs? So this is a connection from the VM to the various backends. And this can be either Mycelium or IPv6. The thing about IPv6 is that the backend nodes need to be reachable. So they both need to have working IPv6 connection and also an open firewall, which most of the nodes on the grid do not. Our nodes in Freeform do. Most other nodes are behind a firewall. So Mycelium is going to be the way to go here. It's also the only way to go due to some ongoing things on the grid right now, whereby IPv6 connections aren't available to ZDBs at all, but that should be coming back at some point in the future. So you can use Mycelium here without needing to have Mycelium on the machine that you're deploying from, because it's only used to connect from the VM to the backends. On the other hand, we also need to connect to that VM over SSH, like I was saying before. Again, we can use Mycelium or IPv6. If you have IPv6 on your machine, and again, your VM must have IPv6 available. The node that your VM is running on must have IPv6 available, and the firewall must be open. So in this case, my VM node is also in Freeform, so I can reach it over IPv6. But if that's not the case, you can use Mycelium, but then you need to have Mycelium installed and running on the machine that you're creating the deployment from. It could also be possible to use WireGuard here, but it somewhat complicates the automation, let's say, because the way that you set up a WireGuard connection is different on the various platforms, and it usually requires root. So it's much simpler to use an existing Mycelium connection or use IPv6. If you want to use this and you need WireGuard for some reason, then there can probably be a way to make it work, but I didn't build that out yet. So yeah, I'd say get set up with Mycelium if you need a way to connect to your VM and you don't have IPv6 available either on your local machine or on the node that you're deploying your VM to. All right, so that's that. Next, let's look at the other required config file that we'll need to copy and edit. This is our Zstor config, and what we're actually supplying is a base config. So I've just added in some extra words in here to make sure we keep these files straight. The base config, what that means is that our deployment script is actually going to add the information about the backends that as Zstor needs, and it's going to do that automatically based on the information that comes back from the deployment. So our deployment script is going to create those ZDBs based on the node IDs and the sizing that we gave. It's actually going to automatically generate a random password, and then it's going to put all that information into a config file using this as the base or the stub, and then filling those items in below. It's also going to automatically generate an encryption key and put that in here. So this is the stuff that we can't automatically determine, and it's also not fixed. So in particular, the things that are most relevant are going to be up here, minimal shards and expected shards. So to understand more about how the minimal shards, expected shards, and the group settings, the redundant groups, redundant node settings work, you can check in the documentation. The redundant groups and redundant nodes are not required, so we set these to 0, they'll just be ignored, which is what we'll do for the demo today. Minimal shards is the number of nodes, number of backends that need to be available in order to reconstruct data. So in this example, we have 4 backends, and we want to be able to use 2 backends to reconstruct our data. Expected shards is the number of backends that the data will be written to. So in this case, we have 4 backends in our .py and what this means is that anytime we write some data into this Zstor system, it's going to try to put that data into all 4 of those backends. And when we want to reconstruct data from the backend, we'll need to have at least 2 of them available. Now, we can do, the expected shards doesn't have to match the number of backends that we have, so we can end up with more complicated arrangements where we have 8 backends and 4 expected shards. In that case, Zstor will choose 4 of those 8 and write those 4 shards. It will still write 4 shards because that's the expected number. Those will go into 8 of the backends. Now it comes time to restore that data. We need to have at least 2 of the 4 that data was written into available. So it makes our life a lot more complicated if these expected shards and the number of backends that we're using don't match. So that's one thing to keep in mind as you are setting this up. It's much simpler to reason about if those numbers match, and then you always know that if, say, one of your backends goes down, then you'll know where you stand in terms of your ability to rebuild that data with regard to everything that's stored in the system. So again, there's more information in the documentation about sort of how to set this up, and I think also about how to calculate your overhead for a given arrangement. In this case, it's pretty simple. Our overhead is going to be 50% because we are generating twice as many shards as we need for each piece of data. All right, so the stuff down here is stuff that should not be edited unless you know what you're doing and can also edit the relevant files over here in like Zenit and scripts. So you can generally just want to leave this alone unless you're diving in deeper and want to do things like change your mount point or change where your data is stored. But for most cases, don't need to worry about that. The last thing that you might want to edit is the ZDB data directory size. This is the size of the front end. And once we get this much data in megabytes, in this case, it's about 200 gigabytes. Once we get this much data into our front end, that's when Zstor is going to start deleting data blocks that are stored in the backends in order to keep our front end size below this. So 2.5 gigabytes is actually pretty small. My VM is much bigger. It's just an example value. But this is how you can control the size of your front end and control at what point Zstor automatically starts removing data blocks as that front end data grows. Now, there's some other stuff in here that I want to just quickly show you. We have the Zenit section, which defines all the services. You don't need to worry about this under normal circumstances, but if you want to tweak anything, things like the ZDB data block size, when ZDB is rotating its data blocks and things like that, that's going to be in these files here. Scripts, you can check these out if you want. Like this is how we set up the VM automatically. The main one that you might actually need to execute one day would be recover.shell. But the deployment script is always going to, the Pulumi deployer is always going to take care of either uploading those scripts into the VM and running them on your behalf, or uploading them for you. In the case of recovery, you have to execute the script automatically, just because that's a stage where it's good to be hands-on, basically. So I didn't fully automate that step. But if you're curious about how the system works, you can jump in and check out those scripts. This prep VM might also be useful if you wanted to manually, or if you wanted to set up your own machine, your own Linux machine. You might be able to use that script, or at least look at it for some inspiration. All right, the last example file that we have here is the Prometheus config. This is optional, as I mentioned before. The Pulumi deployer it supports exporting the metrics from Zstor and also node exporter metrics. So these are metrics about what's happening in the VM in this case, CPU usage, memory usage, things like that. So if you want the deployer script to install Prometheus, install node exporter, start all that stuff up, then you just need to drop in your prometheus.yaml or copy this file to a new file called prometheus.yaml, edit it to your needs. Zstor exposes some metrics, both about the front end and the back end. I'll show you a dashboard I built that helps you visualize some of those metrics in just a minute. But the important things that you might need to edit here would be especially this remote write block. So Prometheus is a scrape-based system, which means Prometheus is running somewhere and it reaches out and pulls metrics back towards it. So in this case, what we have is inside our VM, we have Zstor running, we have Prometheus running. That Prometheus is scraping from that Zstor and also from that node exporter. But it's in the same VM, and we want those metrics to be available somewhere else next to our Grafana instance in this case. So we're using a remote write feature in Prometheus to send all those metrics that this local Prometheus is scraping into another Prometheus. And in the case of this demo, I'll be showing how to do that with a Grafana cloud instance. So Grafana has a nice free plan on their hosted instance, which includes a Prometheus that you can remote write your data to, and then it will be available inside that hosted Grafana. So that's what I'll be showing in the demo. You can also host your own Prometheus and your own Grafana if you want to. In that case, this remote write URL would be wherever your Prometheus happens to be. The important thing to note here is that this URL needs to be accessible from the VM. So if it's not reachable on the public internet, then you need to take care of whatever kind of private networking or however you want to set that up, such that your VM is able to reach out and perform those remote writes. There's other ways you could set this all up. For example, you could have a remote Prometheus actually scraping sort of from a distance, but I'm not going to cover all the details about how to set that up. This is a fairly simple case where you can just come in here, provide your URL, username, and password, which in the case of Grafana Cloud, these are provided to you from Grafana. And then the deployer script will take care of the rest and make sure that your Prometheus is up and running, configured, and exporting that data. If you want, you can also edit these job names. So these are how the data shows up inside, say, inside Grafana when you want to visualize it. This push gateway is something that I'm working on. I won't actually show in the demo, but it's a way to visualize a bit more data. So maybe in a future video, I'll have an update about some additional things I'm working on here. All right, and the actual deployment script is in here. So this is in Python using some Pulumi constructs. It's about 340 lines, which is not bad if you want to have a look, try modifying some things. There's some stuff that's not exposed yet as in this vars.py file, which I should probably move over there. Things like the amount of CPU and RAM in your front-end machine. So if you need to edit that, you can come in here and edit this file to, say, beef up that VM if you want to. I should probably move that into vars.py as well. But yeah, have a look through here if you're curious about how the deployer works. Final file in here is pulumi.yaml. And this includes a deployment name, which Pulumi uses to segment its stacks, which we'll see later. So stacks are a way, like if you want to do the same thing on testnet and mainnet, you can do that with stacks. This deployment name, any deployments using the same name will show the same list of stacks. So it's just something to keep in mind. Like if you want to play with multiple deployments, if you change this name, then you'll have isolation there, and you won't have all your same stacks showing up in every deployment that you do. Just a note, so if you're running multiple deployments, you might want to edit this name and give it something descriptive along with editing your those Prometheus names. So those are the things that the places where we have names that you might want to make unique if you're making multiple instances. Alrighty, so that's run through of all the files that we have in here. There's also some tests. I won't say more about that. That's just some automated tests I'm working on. Let's go ahead and jump into the terminal and create a quantum safe file system deployment. All right, so here I've already installed Pulumi on my system. I've set my mnemonic and environment variable, and I've cloned the repository, and I've also made my own vars.py, my own Zstor base.toml. I've also got a Zstor binary in here, in case you're wondering. If you drop your own Zstor binary into this folder, the deployer script will use it. So if you want to build out, the bleeding edge features, you can put your own binary in here and it will be used. If you don't include one, it will automatically grab the latest binary release from GitHub. And yeah, I also have a Prometheus.yaml. Let's look just briefly inside these config files. So vars.py. What I'm doing in this case, like I showed before, we have four metadata nodes. Four data nodes are the same, but I also have a second set of data nodes. So what I'll be doing in this case is replacing a couple of the data nodes and showing you what happens when we do that. I also have some other sets of data nodes that I've been using for other tests. These are just commented out, so anything with comment won't actually be used. And I'm going to be using my Cilium for the backend connections. Pretty much everything here is otherwise is like I showed in GitHub when I was walking through these files. Let's check Zstor config base. So this is just identical to what's in the example file. And finally, I won't show you the Prometheus file because that contains username and password, but let's just say that that's got those three fields filled out from the remote write block like I showed you before. All right, so actually let's jump back here just to the documentation so that you know that you don't need to remember these steps. They are shown here. So This is all the stuff about the config, which we just walked through. Now, how to create a deployment. So the first thing you need to do is log in. On my system, I'm already logged in. Once you've done that, you can write Plumi up. So let's do that now. And now we have the option to choose a stack or create a new one. So in this case, I've been testing with this setup. So I already have an existing stack called demo, but if you're doing this for the first time, you won't. Let's make another one called demo2. And you can enter a passphrase to protect your config and secrets. I'm going to leave this blank for now. As we'll see in a minute, this deployer is going to save a copy of your Zstor config to your local machine, as well as uploading it into the VM. And that's actually where your secrets are going to be stored. So using this passphrase to encrypt the secrets is not going to do a lot of good because they're also going to be in plain text on disk. Now, Pulumi has created a plan for what it's going to do here. So we can see that it's going to create these ZDBs. It's going to create the VM, yes, VM, and it's going to copy some files to the remote machine, and it's going to run a couple of scripts on the remote machine. So it's also going to generate our encryption key and our password. So we can see pretty much everything that's going on here. We'll have a network to put the VM inside of. And yeah, that's pretty much it. That's showing us the full plan. And I can go ahead and hit yes, and it will start to create the deployment. This normally takes a couple of minutes from start to finish. So while that's happening, let me just get back to telling you about your Zstor config file, which you will find on disk. So as I was saying before, this deployer, it takes that base config, it's going to add the encryption key and the backend information, which is everything that Zstor needs in order to function. That config file is the one thing, the one and only thing that you need, and also that can be used to recover the data stored in the backends. So this is sufficient to recover the data, and it's also necessary. What that means is that if you lose this Zstor config file, if you lose all copies of it, including the one in the VM and the one on your local machine, then you won't be able to recover the data from the backends. So what I highly recommend that you do is you take this config file and make another copy of it somewhere safe, somewhere like your password manager, or maybe in some kind of offsite backup that is encrypted with a passphrase or a password of some kind. In theory, anyone that gets this file can download and reconstruct your data. Of course, they would need to be pretty savvy about how to use things like this deployer in order to do so. So maybe that's not a huge risk, but you should keep this file safe and secure and make sure that you don't lose it. And that's my spiel. All right, so our deployment is successful. We've received both a mycelium IP address and a IPv6 address. I'm going to use the IPv6 address because I happen to have IPv6 and we can use it in this case. So this tends to be a nice, reliable, and well-performing way to do things when it's working. All right, so now we're inside of our front-end VM. First thing that we should check out here is our mounts with df. So we'll see that we have a ZDBFS mounted at mount QSFS. So this is where we can read and write files from our Quantum Safe Storage System front end. And when we do that, the system will also write them into the backend. So let's do a little test here. What I have here is an Ubuntu Cloud Images site open where we can download some Ubuntu Cloud images. I'm just using this as an example because Ubuntu is reliable, and these files are of a good size to kind of give us a nice demo. This could be any data, so just fill in the blank here. I'm going to switch folders into that mount point, and I'm going to start to download this file. So what we'll see is that, we can write data into our front end at a pretty good rate here. And probably the main thing limiting us is actually internet bandwidth. But this file is coming into our front end. And while that's happening, let's take a look at our metrics. So our metrics are already available here. Let me back up. So this is my hosted Grafana instance in Grafana Cloud. I've got a folder here with a couple of dashboards that I use for my quantum safe deployments. One is Node Exporter, which is a very popular publicly available dashboard for visualizing node exporter metrics. So those are, like I was saying before, things like CPU, RAM, and disk utilization. The other one is our QSFS storage metrics. This is a dashboard that I built specifically to visualize metrics coming out of Zstor about the QSFS system. So let's take a look. I'll show you the node exporter quickly. Again, this is a standard dashboard that you can look up. We'll see things here like the CPU usage rate. We're just getting our first couple data points in here, how much RAM is being used. So this is just a way that you can keep an eye on your VM and see how it's doing. You could set up some alerts around this. So like if you want to know if your front end is down, you could get an alert when this data becomes unavailable, things like that. The other dashboard is the one that we'll be spending more time with, and I think it's more interesting. This is the one specifically showing us information about our quantum safe file system deployment. So up here at the top, we can see a quick overview of the most important things. How many healthy data backends we have. In this case, it's going to be 4 out of 4. How many healthy metadata backends we have. In this case, it's also 4 out of 4. How much total data usage we have in our data backends. So this is just the amount of data that we stored divided by the amount of storage that's available. Same figure for our metadata. It's unlikely that you would fill up your metadata, but you can keep an eye on it here. Then we have a read and write rate. So you can see how much data is coming in and going out of the front end. So, if you're using this system in such a way that you have some different services that are reading and writing, you could come in here and just get a feel for what is the current utilization rate for inbound and outbound data from the front end. So our connection statuses, so we have the overview, connection status overview here. They are graphed out individually here for both the metadata and data. So at this point, we can see that all 4 of our backends, data backends, are reachable. If any of them became unreachable, there would be a line down here at the bottom for unreachable. And then we can also see them here. We can see their last state, and we can see their namespace. So when we create this deployment using the deployer script, it's going to write the node ID into the namespace. And so if we have a backend going down and we need to replace it, we need to check the node ID to know which one we need to replace. We can see that here as part of the namespace name. All right. Down below, so this is a time series graph of the data coming in and out of the front end. So that corresponds to those gauges that we saw in the upper right hand earlier. Here we have our metadata usage graphed out in more detail. So these are usually going to just all stay synchronized as that metadata is coming in. And then finally, we also have the data in more detail. So let's go ahead and refresh and see what's going on here. So sometimes if we zoom in, we might be able to see some distinction, but actually in here, our data backends are moving quite in lockstep. So these are actually 4 lines that are all on top of each other, showing us that we've started at 0 here and we've written data into our backend. So there's 287 megabytes in each backend, and this has leveled off here. So as we wrote that data into our front end, Zstor started to upload it into the backends, and once it finished its job, then we see that we've hit again like steady state here. So there's no more data being written into the backends at this point in time. And we can also see here that our front end data, so basically our download is finished, and we've stored all that data into our backends. All right, so that was fun. Let's have a look at what happens if we need to replace some backends. So I'm going to disconnect from this SSH session in the VM, and let's go ahead and edit our vars.py file. As I said before, I have a second set of data nodes here. So what I'm going to do is just comment the first set, uncomment the second set. And this is basically just editing our set of data nodes. I'll save this file and I will run the player again. So yep, and I'll choose the same stack, demo2. It's going to make a plan for what to do next. All right, so we'll see that we are creating 2 new deployments. We are updating 2 deployments. So since our metadata backends will still be running on these nodes, this is why they're updating and not totally destroying these. More realistically, if these nodes went offline, we would be changing the data and the metadata backends, but for the purposes of the demo, I'm just changing the data backends. Let's go ahead and perform this update. While that's happening, I want to head back to the documentation quickly and show you the segment here about replacing backends. So when you replace backends, this is, well, the first thing that is important to note is that this is a destructive operation. So if you come in and you replace all of your backend node IDs with different ones and run this operation, all your data will be lost. So you need to be careful about this. Only replace backends that are down and that need to be replaced, because the old ones will be decommissioned. After you've run the deployment script, there's an additional step that's needed to cause Zstor to actually start using the new config. So the deployment script will it'll generate a new config file. It keeps a backup of your old one, generate a new config file. It'll upload that into the VM, but we'll also need to connect to the VM over SSH and instruct Zstor to start using the new config file. There's 2 ways to do this. One is called hot reload, which means Zstor continues running. The other way is to restart Zstor. There's actually a small bug in Zstor where the metrics, it continues showing metrics from the old config if you do the hot reload. So until that's fixed, I think the better thing to do is actually to restart Zstor. So that's what I'll show you here. All right, so our update is complete. And if I look here, what I will see is that right now this file is the same as this file. And if we do another update, we'll have version 3, and then this would correspond to version 3. So that's what's going on there. And the latest copy will also be in our VM. So let's connect via SSH again to this VM and go ahead and restart Zstor, as I was mentioning. So if I look inside ZNet, we can see we have a Zstor service here. So what I'm going to do is ZNet stop Zstor and ZNet. So that will restart Zstor. Let's take a look at our metrics and see what happens next. So let's go back to just checking the last 15 minutes. As we can see, we have two backends that are unreachable. So that's what happened when we decommissioned those backends. They went to unreachable. So if something happened, this is where you would be able to see, like if a node went down, it's one of your backends, you'd be able to see it here. You could also set up some alerts, like in Grafana here, we can just set up alerts. So say we could set up an alert on this healthy backends gauge metric, the same calculation here, and say, oh, if we go below 100%, like fire an alert, something like that. So then you can get the alert and take action by deploying new backends. We should be able to see here. So that's still showing our old IDs. Let's refresh again. Okay, so now what we can see is we have, so these old backends are no longer in the metrics after we restarted Zstor, and now we have 4 healthy reachable backends. So that's great. And if we go up here, we're back to 100%. So by changing that config file, by running the deployment script again, and then restarting Zstor, we have restored ourselves to a nice, happy green place. So let's look down here and see what's happening with our data usage. So unlike the connection statuses, the data usage metrics for unreachable backends are simply removed. So what we can see here is we had 4, and then when we decommissioned the 2 backends, but before we restarted Zstor, now we only have 2. So that's one thing to note about these metrics. If some backends are unreachable, they'll simply be removed from, say, the data usage. And then when the new ones came up, we can see that we now have 2 new ones with 0 bytes used, and those are now down here on the bottom. So when we change the Zstor config, Zstor is periodically running its checks to basically see, like, do the stored files have the desired, do they have those expected shards that we configured available in healthy backends? And if they don't, then it's going to attempt to run a repair operation that will restore that. So let's see if we can detect any repairing happening already. It's not yet. So this repair process runs on a timer, so we can see it hasn't been triggered yet, but it does work automatically. So let's just give it a sec here and see if we can observe this repair cycle happening. We're doing our remote write every minute, so every minute we get some fresh data in. We don't see the repairs happening yet. While we wait, let's go ahead and check out our Zstor log file. So in the normal course of operation, you shouldn't need to look in here, but if you're curious or you think you have a problem or maybe you found a bug or something like that, you might want to look in this log file. The deployer is putting some logs under var log, and so we actually have some logs from like our scripts that we're running. We also have a Zstor log file here. So let's just print that. See what's going on. So we can see some things happening here, like our store operations, restoring files. When our repair operations happen, we should be able to see those as well. Here's where we restarted Zstor. And if we have some repair stuff happening, that might be these store commands that we see here. So this log file is a bit dense, but I just wanted to show you that it's here. And if you wanted to try to get more insight into what Zstor is doing, you can have a look in there. Let's see if we're using any more storage in our backends. So we can barely see it here, but we do see there's already a few kilobytes being written into those backends. And now the repair operation has finished. It took a few minutes to get going, and then we were able to pretty quickly come back to our desired backend config here. So as we can see, the amount of data stored in the two new backends started growing and eventually came back to be equal with the amount of data stored in the original two backends that we didn't replace. So again, we've sort of leveled out here, and that's how we can see that Zstor has finished its work. All of the data that we've stored is now again stored in 4 backends. Those backends are healthy, as we can see here. So we've returned back to our desired state. We have 4 healthy backends. We can always recover from any 2 of them. That is, recover any data that's not still available in our front end. And as I mentioned, I'm not going to show the front end recovery process, but it is ultimately somewhat similar. We just go into our vars.py file, we change that VM, we wait for a new VM to deploy, and execute a recovery script on that new VM once it's ready. And that information is down here at the bottom of this documentation page regarding the Pulumi deployer. All right, so that's it. Thank you so much for joining me today. If you have any questions, feel free to come into our chats on Telegram. The tester chat would be a great place to ask questions about this. You can also always feel free to DM me on Telegram, open an issue on one of our repos, the repos that I showed today, or contact our support team for help, and they can also forward your questions to the appropriate member of the team or help with opening issues on the repos if you found something that needs to be addressed. So hope you enjoyed the video today. Hope you learned something, and I look forward to hearing from you about your experiences with the new QSFS Pulumi deployer. Bye for now.